Section: Introduction. In this section, we discuss the two forms of music: recorded pieces, which we refer to as music as a noun, and live performances, known as music as a verb. Live music is deeply connected to our human experiences of creativity, expression, and social interaction. However, most modern AI systems for music focus on generating audio offline, missing the potential of live music. In a typical offline scenario, we provide control information, wait a certain amount of time, and then receive a set duration of audio. In contrast, our proposed live setting allows us to continuously input control information and receive an uninterrupted audio stream, with a slight delay between our inputs and the audio response. This continuous interaction encourages active creation and personalized expression, highlighting the importance of the process as well as the final product. Yet, achieving the necessary synchronization for high-quality audio generation in real time is challenging for machine learning models. Some offline systems can generate audio in real time, but they often lack the features needed for live performance. We define live music models as those that can generate audio in real time, stream continuously based on user inputs and past audio, and have low latency for responsive controls. Open-weight models are ideal for live generative music since they can operate on users' devices, offering benefits like lower latency, higher reliability, privacy, and customization. Cloud-based APIs provide access to more powerful models but come with trade-offs. To help users navigate these options, we introduce two systems: Magenta RT, which is open-weight and runs on device, and Lyria RT, which is cloud-based. Both systems share a core framework based on codec language modeling. We focus on Magenta RT, which is particularly relevant for the AI research community due to its ability to be fine-tuned and explored for transfer learning. It stands out for its live generation capabilities among open-weight models and outperforms existing offline models in music quality while using fewer parameters. We also provide demos that showcase real-time generation, fine-tuning, and a new interaction method called audio injection. Magenta RT is a codec language model designed to generate high-quality stereo audio in real time based on user-provided acoustic styles. We use a pipeline approach with an encoder-decoder transformer to model audio tokens from SpectroStream, conditioned on style embeddings. In our audio tokenization process, we utilize a codec that converts audio data into language-like tokens. This codec consists of an encoder that transforms raw audio into discrete tokens and a decoder that reconstructs the audio from these tokens, aiming for minimal distortion. We employ the SpectroStream codec, which is a multi-channel neural audio codec, and we adjust its bandwidth for live streaming to achieve a target of 400 tokens per second. Section Summary. In this section, we explore the distinction between static recorded music and live performances, emphasizing the potential of generative AI in live music creation. We introduce our systems, Magenta RT and Lyria RT, which cater to different user needs by enabling real-time audio generation with low latency and high-quality output, while also discussing the technical challenges and advantages of on-device versus cloud-based models. Section: Style Embeddings via Music Co-Ca. In this section, we describe how we utilize a combined audio-text representation to control the overall audio style. We achieve this by training a model called Music Co-Ca, which learns from music that has various textual descriptions. These descriptions highlight musical features that we refer to as style. Our model consists of two parts, an audio embedding tower and a text embedding tower, both mapping to a shared space of 768 dimensions. The audio tower processes a log-mel spectrogram from a 10-second audio slice, while the text tower handles tokenized text with a maximum length of 128 tokens. We use attention pooling to condense the outputs of each tower into a single 768-dimensional embedding, which can then be quantized into 12 discrete tokens. For variable-length audio, we pad it to a multiple of 10 seconds and average across chunks. Additionally, Music Co-Ca includes a text decoder that generates audio captions, although it mainly serves a regularizing function. Our training objective combines contrastive and generative losses, and we optimize the model using the Adafactor optimizer with a specific learning rate and batch size. In our modeling framework, we predict discrete audio tokens based on previous audio and a shared audio text embedding. This approach is similar to Music LM, which is based on Audio LM. We make two significant changes for live generation. We simplify the model by using a single language model instead of multiple ones, and we implement a chunk-based autoregressive method for continuous audio streaming. To generate an uninterrupted audio stream, we predict audio sequences longer than those seen during training. We address potential performance issues by using chunk-based autoregression, where we predict 2-second audio chunks based on the last 5 chunks of history. This method reduces error accumulation and simplifies deployment. We also use a coarser representation of the audio context, focusing on the most important acoustic information while maintaining high fidelity. In summary, we define a chunk as a segment of audio tokens representing a specific duration, and we condition our predictions on a simplified representation of the previous audio chunks. Our main objective is to model the probability of each chunk given the course context and the style embedding. Section Summary. In this section, we describe our approach using Music Co-Ca, a joint audio text embedding model that enables high-level control of audio style through a shared representation, and we outline our autoregressive model, Magenta RT, which generates continuous audio streams by predicting discrete audio tokens based on previous audio and style embeddings. We introduce chunk-based autoregression for efficient infinite streaming and utilize coarser audio context representations to maintain real-time performance while simplifying model deployment. Section: Encoder-Decoder Language Model. In this section, we describe our encoder-decoder language model. To model the distribution, we utilize an encoder-decoder transformer language model trained with T5X, and we provide pre-trained models in T5 base and large configurations. For the encoder, we have a bidirectional component that processes the acoustic history and style control to create an intermediate representation for generation. At each chunk, the encoder takes a combination of the acoustic history and style tokens, totaling 1012 tokens, which includes 1000 audio tokens and 12 style tokens. The vocabulary is unified across the codec and quantized style tokens. In the decoder, we differentiate ourselves from previous work by ensuring a real-time factor of at least 1 for generation, which is essential for live interactive applications. Unlike past models that use hierarchical cascades or delay patterns, our decoder consists of 2 connected transformer modules. The first module builds a temporal context by processing acoustic frames, embedding and aggregating RVQ tokens to create a single frame level embedding. The second module then predicts RVQ indices based on the previous temporal context. With this setup, we achieve a real-time factor of 1.8 on an H100 GPU using the T5 large configuration. For our experiments, we focus on Magenta RT and live music models, which allow for new interaction types best evaluated through direct human feedback. Many design choices were tested through play sessions with team members and partner musicians to optimize the expressiveness and engagement of the instrument. We also conduct more controlled experiments to assess our controls and compare with existing models, focusing on core capabilities like audio quality and adherence to text conditioning, as well as unique features of our live music models, such as generating musical transitions based on changes in the conditioning signal. In terms of training, we pre-train the language model in both base, 220 million parameters, and large, 770 million parameters, sizes. Our dataset consists of around 190,000 hours of mainly instrumental stock music. Each training example is a 12-second audio clip, divided into 10 seconds of context and 2 seconds of target tokens. We derive Music Co-Ca tokens from the target audio, using the first 6 RVQ levels for training. To address cold start issues in streaming, we replace early context tokens with variable length padding. Each model undergoes 1.86 million training steps using the Adafactor optimizer, with a batch size of 512 and a learning rate schedule that includes 10,000 warm-up steps. We utilize TPU v6e hardware, with 128 chips for the base model and 256 for the large model. For sampling, we embed and tokenize prompts using Music Co-Ca, matching the training setup. We sample with classifier-free guidance, applying a temperature of 1.3, a top K of 40, and a CFG weight of 5.0. When comparing Magenta RT to previous offline text-to-music generation models, we keep the text conditioning fixed and generate audio chunks up to 47 seconds long for a fair comparison. We evaluate the quality and adherence of the generated audio using 3 established metrics: the fretchit distance based on open L3 embeddings, the Kullback-Leibler divergence, and the clap score. Our results show that Magenta RT has the lowest fretchit distance and Kullback-Leibler scores, indicating that the generated audio is plausible and closely matches the reference audio. The clap score, which measures adherence to the text prompt, shows that Magenta RT scores between the other 2 models, with the higher score of stable audio open likely due to their use of clap embeddings during training, while we trained with Music Co-Ca. Section Summary. In this section, we describe our encoder-decoder transformer language model, T5X, which processes acoustic history and style control to generate audio, achieving a real-time factor of 1.8 for live applications. We detail our training setup using a large dataset of instrumental music and evaluate our model's audio quality and adherence to text prompts, demonstrating its effectiveness compared to prior models. Section: Generating Musical Transitions. In this section, we explore how to generate musical transitions. Live music models enable us to respond dynamically to user inputs. To evaluate this, we create a prompt transition test where we select pairs of text prompts and ask the model to create musical transitions between them. We gradually blend the Music Co-Ca text embeddings of the starting and ending prompts over a period of 60 seconds, divided into 6 steps of 10 seconds each, using this as style conditioning. We then assess the similarity between the audio output and the conditioning embedding at each moment. We conduct transitions for 128 prompt pairs. As shown in our results, the outputs maintain a strong similarity to the target embedding throughout the transition and effectively shift from the initial to the final prompt. The audio context conditioning results in smooth transitions that blend styles while retaining elements from the original prompts. Although this approach leads to slightly lower similarity at the end of the transition and a minor dip in the middle, it allows the music to evolve smoothly and coherently, making the history of prompts a significant and expressive aspect of the performance. Next, we discuss style conditioning through text and audio. During inference, we can create a target conditioning vector by calculating a weighted average of the Music Co-Ca embeddings from several control prompts, which can be either text or audio. This method allows us to blend styles effectively, as we can combine embeddings from different genres or instruments while controlling their influence. Using a shared audio-text embedding space for conditioning also enables us to use audio prompts to achieve specific musical styles or instruments that might be hard to describe with text alone. Since audio prompts align closely with our training setup, where style conditioning comes from the target audio, this approach is expected to be more effective. Additionally, we can mix multiple audio prompts to create interpolations of various styles or combine text and audio prompts, giving us control over high-level characteristics like genre, style, instrumentation, and mood. Finally, we introduce an audio steering mechanism called audio injection, which allows users to continuously guide the generation through a live audio stream. At each generation step, we blend the user's audio input with the model's output, tokenize this mix, and use it as context for the next generation. Importantly, the user audio is not played back directly. Instead, the model predicts the continuation of a context that includes the user audio. Depending on the injected audio and the desired style, the model may choose to repeat or transform the user audio or be influenced by its features, such as dynamics, melody, and harmony. Further details can be found in the appendix.